Hey guys, this video we are going to discuss Lagrange interpolation polynomials. Suppose we are given a data set, right? So we have n plus 1 number of data points, right? So we are going to find a Lagrange polynomial which passes through these data points, right? That is our goal. So let's see how we do this. All right, so for that we have to define the cardinal functions. So actually these are polynomials, n degree polynomials, right? In x, these are functions of x, right, which satisfy the following conditions, the following property. This one here, let's take one of them. L sub I is one of cardinal functions. So this L of I evaluated at x sub I is equal to delta of ij. What that mean? Let's see what that mean is. So if when I equals j, the delta returns the value of 1. When they are different, the delta returns the value of 0. This delta is called the Kronecker delta, right? So this is called Kronecker delta, right? So now we are going to look at the way of constructing these cardinal functions, right? Let's these cardinal functions can be written as follows, right? So here, look at the definition here. So we consider these terms, these factors. On the denominator, on the numerator, it has x minus x sub j, and on the denominator it has x sub j minus x sub I minus x sub j, right? So we multiply these factors all over from j. J runs from 0 to n except j not equal to I. So let's see what this is, right? So the first one, when you plug this j value into here, we get x minus x sub 0 divided by xi minus j sub 0, and this is our first term. And the second term would be, we have to plug the value of we have to plug j equal to 1. When you plug that one, we get the second term, x minus 1, x minus x sub 1 divided by x I minus x sub 1. So these terms, we write these terms as a product up to x minus up to I minus 1. Okay, yeah, this is the I minus 1. When you plug j equal to I minus 1, we get this one, but we don't write the I term. When we ignore when j is equal to I term, we don't write that term, and we start from I plus 1 term. So this is the term when j is equal to I plus 1 and up to j equal to n, right? I hope you understand this product, right? So how many terms are there? There are n terms, because here, so j runs from 0 to n. That means we have n plus 1 terms, but we don't consider j equals 0, right? We don't consider this case. That means we have how many factors? N factors. The multiplication of n factors. That means this is a polynomial of n degree polynomial. This is a n degree polynomial in X, right? Now let's look at the following results. So if you consider L1 L sub I cardinal function, right? So if you plug this value into that cardinal function, we get 1. The value of L sub I evaluated at x sub I is equal to 1. Let's see. So let's plug this value into this cardinal function. So when you plug this x sub I into here, so into here, what happened? So when you plug this number into here, you get the same factor. So we can see this factor is the same with the factor in the on the denominator, right? So we can cross that off, and we plug this one, that one also can cross that off, and everything we can cross that off, right? Then and ultimately we get this value, right? When you plug this number into this cardinal number, it returns the value of 1, right? All right, that is pretty clear, right? So when you plug any other time, any other x value than x sub I, what happened? So for instance, if you plug x sub 2, what happened? When you plug x sub 1, what happened? So here, when you plug x sub 1, what happened to this factor? This factor becomes 0. Then everything collapses to 0, because one of them factor equal to 0 means the product is going to be equal to 0, right? So if you plug any value of xi which is not equal to I, right, then the cardinal function at that value is equal to 0. So that means what this means. So this one means this cardinal function at xk is equal to coordinate delta function, right? I hope this more sense to you, right? So once we have cardinal functions, right, so we can write out Lagrange interpolation polynomial as follows, right? So Lagrange polynomial can be expressed as this one. So we consider cardinal functions, right? So we sum over all cardinal function, but we have to multiply that by y sub I. So because you have data set, right? So what is our data set? Data x sub 1, y sub 1 is the first, no, starting from 0, right? And this is the first data point, this is the second data point, and this goes up to nth data point. So we have n plus 1 data points, right? So here we have n number of data points. With this we have n plus 1 data points, right? The Lagrange polynomial is equal to the sum of cardinal numbers, not not the sum of cardinal numbers. So we found L i's. Say this is the first cardinal polynomial. It's L sub 0 of x times your value of y's, right? Or your value. What is the corresponding value? Y0 plus, and the next cardinal function times the corresponding this should be 1 here. Yeah, sorry guys, this should be 1. This is this that should be multiplied by this value, and we consider this sum. So this is called the Lagrange interpolation polynomial. And finally we have the nth cardinal function times the value of the corresponding yn. So this is called the Lagrange interpolation polynomial. Pretty easy. This is the polynomial. Let's check this polynomial passes through each data points, like, right? Let's check whether this polynomial satisfies these data points. When you plug one of x, when you plug these x values into here, we have to get the corresponding y value. Let's see whether this satisfies that. So when you plug, for instance, let's plug x sub 0, right, into here. So we know that the cardinal function of this cardinal function L0 evaluated at point x0 is going to be equal to 1, right? So this is 1, but so when you plug this x sub 0 into other places, what happened? That becomes the value of other cardinal functions at x0 become 0, right? Then we don't get these things. We only get this one, right? But the value of this thing at this point is 1. That means p sub n evaluated at x0 is equal to y0. That means this we can say, yeah, this. So this polynomial passes through each point. We can say, we can show that. So this polynomial passes through each data point, right? So this is very easy to compute. So this is the procedure to compute Lagrange polynomial. In my next video, I'm going to discuss an example. So how to find, so if you are given a data set like this, so how do you find the Lagrange polynomial which passes through these data points? Right here we have how many data points? We have 1, 2, 3 data points. So you're going to find the Lagrange polynomial which passes through these data points. All right, see you.